All right, so in this section, section 5.2 of your text, we talk about Riemann sums and integrals. All right, so we saw in the first lecture of chapter 5 that the limit of the form, the limit as x approaches infinity of the sum of f of x of I star times delta x, where x of I star is a sample point on a subinterval. The series expansion turns into this. And so this is how we compute the area under a continuous function. And so we also saw that it arises when we're trying to find the distance traveled by an object. Okay, so areas and distances are computed from using the same techniques, the infinite sum of rectangles. Okay, so this limit occurs in a wide variety of applications when f is not necessarily a positive function. Okay, all right, so we give this limit a name, and we call it the definite integral. Okay, so the definite integral encompasses functions that can fall below the x-axis as well as those that stay above the x-axis. So if a function is defined on a closed interval on the x-axis from a to b, we divide the interval, the closed interval, into n subintervals of equal width. Okay, and the width of a subinterval would be b minus a over n, and we let x of naught equal to a. Then we have x1, x2, x of n will equal to b, will be the endpoints of these subintervals. Okay, so x of naught is here, which is a. Here's x of 1, x of 2, okay, so forth. Here's x of I, so forth. Here's x of n minus 1. Here's x of n, which is equal to b. So here's a to b is split into n subintervals, each of equal width, right? So we let x of I star, x1 star, x2 star be any sample points in those subintervals. So x of I star, okay, lies in the I subinterval. So this would be x of I minus 1. So here's x of I star right here. Right? So this is the refinement of the partition. X of I star is a sample point that lies in the ith subinterval. Okay, and then we define the definite integral of f from a to b is using this notation. And it turns out it's equal to the infinite limit of the sum of the area of a rectangle. Okay, the sums of these areas of the rectangles where x of I is a sample point. The sample point could be the left endpoint, the right endpoint, or any point in between. Could be the midpoint. Could be a random selection. Okay, but provided the limit exists, we have this definite integral. If it does, we say that f is integrable on the closed interval. So this is just a definition. Okay, the definite integral. The word definite means that you have these numbers right here. You've defined your partition. Right? So you'll have these, the x of naught. This is basically your x of naught, and this is basically your x of n right there. Okay? Those two numbers have to be present for the definite integral. All right. And so the evaluation of this limit will give you the area under the curve. Okay, so the precise meaning of the limit that defines the integrals is as follows. Okay, so for every number epsilon, there is an integer n, uppercase n, such that the definite integral minus the sum, okay, minus the sum is less than epsilon if for every integer n, now n is the upper index of the sum, okay, right there. If for any n you choose to be bigger than some threshold, uppercase n, and for every choice of the refinement, or every choice of sample point in the ith interval. Okay. So if you increase this n, make it bigger and bigger and bigger, then there's going to be some epsilon greater than 0, for which the absolute value of these two numbers, the absolute value of the difference of these two numbers will be less than some epsilon. All right, so that's the definite integral, the definition. Okay. In other words, the true value, which is marked by this integral, is approaching the approximating value, which is this summation notation, and it keeps getting closer and closer as epsilon grows smaller and smaller. All right, so that's all that means. So the integral sign, the symbol, this was introduced by Leibniz and called the integral sign. It's an elongated S because the integral is the limit of sums. Okay, f of x is called the integrand. A and b are called the limits of the integration. A is the lower limit, b is the upper limit. And dx has no meaning by itself. Yeah, later on you'll be able to interpret dx as essentially being differential x, which is the width of your rectangle. Okay, basically that's what that means. All right. Okay, integration. All right. So now, okay, so this is useful to know. This right here, the definite integral notation, we consider this to be the variable of the definite integral. Okay, so that's your variable. And as with any function, okay, so what it means is that this is actually a function with variable x. And as far as notation goes, you can replace x in this expression with any other variable, like with t or with r. So that's just a parameter of your integration. As long as you're consistent, if you don't put like an x here and an r here, then you're okay. So this means that you're integrating with respect to r, you're integrating with respect to t, and this integrating with respect to x. Okay, so those are your variables of integration. All right, so basically, long story short, this is a function, another kind of function. The Riemann sum, okay, so we've already discussed this. This is the Riemann sum, the German mathematician whose picture is shown on the class website. Okay, actually his picture is on German currency before the euro came out. Okay. The definite integral is an integral function that can be approximated to within any desired degree of accuracy by a Riemann sum. So the definite integral is basically a Riemann sum taken to an infinite limit. Okay. So the Riemann, if f is positive, in other words, if f is above the x-axis on the interval of integration as shown in this figure, the Riemann sum can be interpreted as the sum of the areas of approximating rectangles. Okay. All right. So the definite integral is the area under the curve y equals f of x from a to b, provided that, of course, f of x is above the x-axis on the interval. Okay. Now, if f takes on both positive and negative values, say like as a cosine function, then the Riemann sum is altered slightly. The sum of the areas of the rectangles that lie above the x-axis and the negatives of the areas of the rectangles that lie below the x-axis. Okay, that is the areas of the gold rectangles minus the areas of the blue rectangles. So that would be your Riemann sum. So effectively, what the takeaway is that we now have a negative area. So these rectangles contributed negatively to the area, a negative area. So in the calculus sense, we have negative areas. Not to be construed as, hey, we have a negative area for some enclosure. No, that's not the case here. It's just for the case of summing up the area under the curve. So you have negative areas. Okay. All right. So we have net area. So a definite integral can be interpreted as a net area. That is the difference of areas. All right, so A1 is the area of the region above the x-axis and below the graph of f, so that would be the golden-shaped areas. And A2 is the area of the region below the x-axis and above the graph of f. So that would be these. Okay, so the definite integral then is the positive areas minus the gold areas minus the blue areas. So it's a subtraction, right? Unequal subintervals, what do we have about that? Though we have defined this definite integral by defining the interval on the x-axis into subintervals of equal width, there are situations in which it's advantageous to work with subintervals of unequal width. Okay, and we can still work with this. So the subintervals don't always have to be of equal width. Mhm. Yeah, nevertheless, if the subinterval widths are delta x1, delta x2, all the way up to delta xn, we have to ensure that all of these widths approach 0 in the limiting process. This happens if the largest width, the maximum of all these widths, approaches 0. So irrespective of how we partition our interval, our x-axis, from A to B, the longest width of the subinterval has to go to 0 in the limiting process. So if we can guarantee that, then we can get the area under the curve. So for unequal subintervals, we can refine our limit to be the maximum, the limit as the maximum of the maximum width of the subinterval goes to 0 of the area of the rectangle problem. Okay, you'll have to do this if you choose not to have equal subintervals. Okay, so what constitutes integrable functions? Yeah, not all functions, of course, are integrable. So which ones are they? If f is continuous on a closed interval, or if f has only a finite number of jump discontinuities, then f is integrable. Okay, so the definite integral exists. If f is integrable on a closed interval, then the limit in definition 2 exists and gives the same value no matter how we choose the sample points. Of course, we've said that. Simplified calculations, we take the sample points to be the right endpoints. So we take our sample point to be the right endpoint for simplicity. If f is integrable on a closed interval, okay, there's the definition again using right endpoints. Delta x is equal to b minus a over n. X of I is equal to a plus I delta x. That's assuming this formula right here arises where each of the subintervals on your partition have the same width. Okay, so we're no longer talking about uneven widths, varying widths of the subintervals. All the subintervals have the same width, namely delta x, which is b minus a over n. Okay, so these formula would be very useful to memorize, and better yet, to understand. All right, so for example, express the limit as n approaches infinity of x sub I cubed plus x sub I sine x sub I times delta x as an integral over the interval 0 to pi. Okay, so let's see how that's done. So from 0 to pi, that means what? Our interval starts at 0, our partition starts at 0, ends at pi. Okay, and then we would want x cubed plus x sine x. Okay, there's your function. That would denote the height of the rectangle, and then differential x. So there's your definite integral, like so. Okay, and there it is, right there. Okay, so in general, we write the limit as n approaches infinity of the sum fx of I star delta x. So in this case, x of I star is a sample point on a subinterval, and the widths of the subintervals are all equal. So we replace sigma by the integral sign, x of I star by x, delta x by differential x. So that's the technique for converting from a limit to an integral. So evaluating integrals. Enough theory. Let's do some problems. Okay, so to evaluate definite integrals, we need to know how to work with sums. Okay. Okay, so these are useful equations right here. So this sigma notation, what this means is, okay, again, the sum of the first n integers can be represented as this term right here, n times n minus 1 over 2. So for instance, let's take n equals 5, for instance. So if n is equal to 5, okay, what this means is, okay, we start at 1 plus 2 plus 3 plus 4 plus 5. Okay, so for n equals 5, that's what this means. And then if you sum up these numbers, it'll be what? 3, 6, 15, right? All right, now if you were to take 5 and you were to plug it in here, that would be 5 times 5 plus 1, which is 6, over 2, which is equal to 15. So this is the closed form representation of the sum of the first n integers, n times n plus 1 over 2. So I would bookmark this formula or write it down somewhere. You'll need it for WebAssign. Then, of course, the next formula we've seen already, the sum of the first n squares. Okay, the sum of the squares of the first n integers. That would be probably the next, would be my guess. Yeah. So here are the sum of the squares of the first n integers. We've seen this already. And then we have the third formula, which is the sum of the sum of the cubes of the first n integers is this as well. So for instance, let's consider the sum of the first 3 cubes. So this would be represented as 1 plus 2 cubed, which is 8, plus 3 cubed, which is 27. Okay, so that's equal to 36. Now if we were to plug 3 in for n, that would be 3 times 4 divided by 2 squared. And of course that's 36. Okay. And the proof of this, of course, you would have to use induction, which is demonstrated in Appendix C of your text. All right, so these 3 sigma formulas, these closed form, will be used to evaluate the integrals, or the sums, that is. All right, so perhaps there's an example that follows. Okay, so, okay, oh yeah, some properties of the sigma. Okay, sigma notation. So if C is a constant, then the summation from I equals 1 to n of the constant means you're just adding the constant to itself n times, so that's n times C. When you have a sigma notation, a constant times a variable that you're summing over, you can factor the constant out. The sum of a sub I plus b sub I would just be, you can take the sigma operator and distribute it in a sum. Or a difference. Okay, so these are some important properties of sigma notations. Again, all of which are proved by induction. All right, so evaluate the Riemann sum for f of x equals x cubed minus 6x, taking the sample points to be the right endpoints, and a equals 0 to b, a equals 0, b equals 3, and n equals 6. Okay, so we want the R6. So basically, what this is asking us to do is an R6. So we want an R6 for f of x. And then we want to evaluate the true area. We want to calculate this definite integral right here. Okay? All right. So far, so good. So the R6 first. So if n equals 6, the interval width would be b minus a over n. And we chose b to be 3, a to be 0, so our delta x will be a half. So that we'll have 6 right endpoints starting at a half. Okay, half. So basically, sometimes it might be helpful to visualize the partition. So in this problem, we start at 0, we end at 3. Okay, and this would be your x of 1, x of 2, x of 3, x of 4, x of 5, and then x of 6, which we'll take to be 3. Okay, I'm trying to make them look equal, so I'll erase this 3 right here. This is your x-axis. All right, and so x of 0 is 0, so 0 plus 0.5, so there's 0.5 right there. This would be 1, 1.5, okay? And these would be the points at which you calculate the heights of the rectangles, like so for your R6. Okay, so you see, I think you understand how that works now. So R sub 6 is equal to the function evaluated at the sample point, which is the right endpoint, times your delta x. We said that the delta x is a half. So in calculating R6, we get a negative 3.9375, which is plausible because most of the area of this curve lies below the x-axis. So it was done just the same technique, using the same technique from the first lecture, 5.1. So the Riemann sum does not represent the sum of areas of rectangles. Okay, so in this case, the Riemann sum does not represent the area of the sum of areas of rectangles because the area of a rectangle is a positive number, and the Riemann sum is negative in this case. Okay, so now let's see what's next. So what the Riemann sum represents is the sum of the areas of the gold rectangles, those above the x-axis, minus the sum of the areas of the blue rectangles below the x-axis. So here's the graph of x cubed minus 6x, and you can see most of its area will lie below the x-axis, and we consider that to be a negative area. Okay. So with n subintervals, we have, okay, so now we do the generalized case. Instead of 6 subintervals, we'll have n subintervals. So again, your delta x for each subinterval having the same width would be 3 over n, because b is 3, a is 0. So x0 is 0, x1 is 3 over n, x2 is 6 over n, x3 is 9 over n. And so in general, the right endpoint is calculated as I times delta x. So it'll be 3i over n. So that's your x of I. So remember that quantity. Since we're using the right endpoints, okay, we can use the right sum, which is what theorem 4 is. So the definite integral of x cubed minus 6x dx is equal to, by definition, the limit as n approaches infinity of I equals 1 to n of fx of I times delta x. Okay, so we replace x of I. X of I is equal to 3i over n. It's just I delta x, right? Zero, x sub 1, it's delta x. Okay, x sub 2 would be 2 delta x. X sub 3 would be 3 delta x. Okay, x of I would be I delta x from 0. Okay, so I delta x, and then delta x, of course, is just 3 over n, b minus a over n. So now we take this 3i over n and we plug it into our function. Our function was what? X cubed minus 6x was our function. Okay, so we take the 3i over n, plug it in to f, okay, and so there's our sum. And since we're summing over I, okay, you see the index of summation is with respect to I. This 3 over n, now from those table of sums that I showed you before, this could be considered a constant. And so this is your C. This is your A sub I is right here. So you can take the constant out of the summation operator, but not out of the limit operator because the limit variable is n. So taking the 3 over n out, you'll have this. Okay, and then so we go ahead and complete the cube. So this would be 27 over n cubed I cubed minus 18I over n. Okay, and then of course now we can take the sum and distribute it with respect to subtraction. It'll probably be the next step. Okay, so yeah, so we took the sum operator and distributed it with respect to subtraction. We could take the factors on I cubed out, the factors on I out, and so we have this result. And then what did they do next? Oh, and then okay, so let's do this. Let's take, let me see if I can extract this illustration here. Yeah. So let me take this down. Let me just delete this. So for reference purposes, what we'll have, I'll write the last equation for reference. So the limit as n approaches, well, okay. What they're going to do next is they'll take 27 over n cubed out. So they'll basically distribute the sigma operator, and then they'll do a number of, well, I don't want to skip too many steps because I'm sure many students will get confused over this. Limit as n approaches infinity. So I'm starting from the last expression. 3 over n. So if we distribute our sigma operator, we'll get this. Okay, so with sigma you can distribute it with respect to subtraction. Like so. Okay, and now this becomes the limit as n approaches infinity of 3 over n. Okay, we can take the 27 over n cubed out of the summation because we're only summing over I. And we can take the 18 over n out because we're summing only over I. Like so. And then we can bring our 3 n's back in. So this would be the limit. The limit as n approaches infinity of, what's that, 81 over n to the 4th times the summation I equals 1. I'm multiplying 3 over n by each of these terms in brackets now, bringing it back in. Okay. And now what I'll do next is I'll replace the sigma notations with their closed form solutions. So we said that all right, well, we'll just pick up with the next slide. Okay, so that's where this comes from. So let me see if I can copy this. All right, so we have this. Okay, so now we'll go on to the next slide. So we got this, right? So compare and contrast. So now we know where this equation comes from. I just showed you in the previous development, okay? So we carry forth. We replace I sigma sum from I equals 1 to n of I cubed with its closed form expansion. I showed you those expansion formulas earlier. And then we replace the sum from I equals 1 to n of I with its closed form expression right here. And then we go ahead and simplify this term algebraically right here. We go ahead and do the multiplication, and simplifying it, it becomes 81 over 4 times 1 plus 1 over n squared. And then we do this multiplication right here, and we get this result. So now we have the limit here, and we can use the limit operators from Chapter 2 to figure out what this limit is. And so the limit becomes 81/4 minus 27, which is equal to negative 27/4, which is equal to negative 6.75. So that would be the true exact area under the curve. And you can compare that with our midpoint approximation. Or I think our R, what do we use, R5 or so, R4, whatever the previous example was. Okay. Okay, so this figure illustrates a calculation by showing the positive and negative terms in the right Riemann sum for Rn equals 40. Okay, so there's 40 rectangles drawn. Okay, and as you can see, as n increases, the number of rectangles increases. You can see we get closer and closer to negative 6.75. Okay. Okay, set up an expression for the integral from 1 to 3 e to the x dx as a limit of sums. All right, so let's do that. All right, so f of x is equal to e to the ax. A is 1, b is 3, so delta x is 2 over n. So x naught is equal to 1. We're going to use the okay. Looks like we're going to use the left Riemann sum here, the left sum. So a is equal to 1. So they take x naught to be 1. X1 would be 1 plus delta x. Okay, x of 2 would be 1 plus 2 delta x. X of 3 would be 1 plus 3 delta x. X of I would be 1 plus I delta x. Okay, so those would be the left sample points, the left endpoints, the left endpoints. Sample points would be the left endpoints. Delta x is 2 over n. So the integral from 1 to 3 of e to the x dx expressed as an infinite limit of a sum of areas of rectangles. Okay, so we replace x of I with its representation from the previous slide. Delta x is 2 over n, and then we replace f with its definition, which is just e to the x. Okay, and then we can take the 2 over n out of the sum because we're only summing over I. So we converted a definite integral representation to a limit of a sum. And now I'll have an expectation that you can go the other way. In other words, take this sum right here and convert it to a definite integral. You'll have some Webassign problems to deal with that. Just remember that this is your delta x. This is your x of I. Okay, this will be your x argument. You have your function, and yeah, you'll have to determine the interval of integration. So you'll be given information that'll allow you to calculate 1 and 3. Okay. Okay. Okay, so don't worry about that. Okay, so evaluate the following integrals by interpreting each in terms of areas. Okay, so we can do, well, obviously, the first one is just, if we look at the function, the for part A, the square root of 1 minus x squared is just from 0 to 1. That's just a quarter circle, right? So knowing that x squared plus y squared is equal to 1, so y is equal to the square root of 1 minus x squared on 0 to 1. So that's just the area of this quarter circle. So the area of a circle, of course, is pi r squared, with r being 1. So this is just 1/4 the area of a circle. So this would just be pi fourths. So that's pi fourths. And then this is just for part B. That would just be what, a line. So at x equals 1 we have 0. At x equals 0 we have minus 1. So this would be the line from 0 to 3. Okay, so you have two triangles right there. Just sum the areas of two triangles. So we'll see those in the next slides. Okay, so there's your quarter circle for part A. All right, and it's just 1/4 the area of a unit circle. Okay. And then for the line problem, I guess I'll show you a graph, right? Okay, so the area of the two triangles, so it would be area 1, which is the area above the x-axis, minus area 2, the area below the x-axis. So area 1 would be 1/2 the base, which is 2, times the height. Okay, so plug in 3, and you determine the coordinate of this point is 3, 2, so that would be the height of this right triangle. So 1/2 base times height, which is 2. And then you subtract off the area of the blue triangle. So 1/2 base, which is 1, times height, which is 1. And so that would be 1/2. So 2 minus 1/2 is 1.5. So that would be the evaluation of this integral. All right. So now we can do the midpoint rule. So back to, and I think we've already talked about this. The sample point is being the midpoint of the interval. Okay. And so in this case, if you use the midpoint rule, your sample point will be designated with a bar, which means the average of the endpoints of the interval. Use uppercase M. Okay, so we can approximate the integral as a finite sum of rectangles where x of I is the midpoint of the interval. Okay, so here it is. Delta x again is the same, but your xi bar is the average of the endpoints of the interval, of a subinterval on your partition. So it's the midpoint of the interval. Okay, so you'll have Robison questions which ask you to use the midpoint rule to calculate the areas on the curve. So, so use the midpoint rule to evaluate this integral. So with n equals 5 from 1 to 2, so we start at 1, okay, and we end at 2. So delta x will be what? 2 minus 1 over 5. So that would be 0.2, right? So 1.2, 1.4, 1.6, 1.8, and 2. We'll put 2 here. All right, so here's 1.1, 1.2, no, I'm sorry, not 1.1, 1.2. This would be 1.2, 1.4, 1.6, and 1.8. Okay, and then, okay, so this is your partition, and then the sample points would be the midpoints. So 1.1, 1.3, 1.5, 1.7, 1.9. So the green hash marks would be your sample points right here. And so you use these sample points to plug into 1 over x, which is your function, to get the heights of the rectangles. And then the interval widths are all the same, which are just 0.2. Okay, so that's all that's going on there. So delta x is 1/5. So delta x, so the integral, the definite integral can be approximated as delta x times f at 11, 13, 15, 17, 19. Okay, so it's approximately 0.6919. And of course, the true answer, I think we've talked about this before, the natural log function, this would be essentially the natural log of 2. Remember how we calculate the natural log? If you have the positive branch of the hyperbola 1 over x, okay, and here's 1, and here's x, then the natural log of x is the area under this curve. Okay, so that's one way of, that's actually the definition of the natural log function. Okay. More midpoint rules. So here they show graphically. Okay, there are the rectangles drawn. Okay, and they apply the midpoint rule to the previous example we worked. They use 40 rectangles. Sample points were the midpoints of each of the intervals. We had 40 intervals, so at R40 was 6.3988. M40 was negative 6.75. So the M40 is closer than the R40, just for this function. It's not true in general. Okay, this important rule is if you change the bounds of the definite integral. Okay, so if you reverse a and b, then delta x changes from b minus a over n to a minus b over n. So you basically have a negative delta x. And so by reversing, if you go from b to a as opposed from a to b, as in the case here, you essentially change the sign of your definite integral. So you change the limits of your, if you swap the limits of your definite integral, you change the sign, okay, and you proceed to evaluate the definite integral as you did before. If a equals b, of course, then the width of your rectangle is 0, so you have no height, and so your definite integral goes to 0. So these are two important properties that we'll use quite heavily later on in this chapter. Okay, so properties of the integral. Okay, so very important stuff here. The integral of a constant, okay, is just equal to, well, c is just the height, so you have a constant height times b minus a. Okay, so the integral of a constant, the definite integral of a constant is the constant times the width of the interval, so which is b minus a. The definite integral of a sum, okay, you can take the definite integral operator and distribute it term by term. This holds for differences as well. The definite integral of a constant times a function, you can eject the constant from the evaluation of the definite integral and evaluate the definite integral with respect to the function without having to carry along a constant multiplier. Okay, and the assumption, of course, is that f and g are continuous functions. Works just like the different derivative operator. So I guess this would be a proof of property 1. The integral of a constant function is the constant times the length of the interval. Okay, probably show you a picture of that. Yeah, so here's y equals c. The area under the curve y equals c from a to b. It's just a rectangle, right? Width times height. Height is being c. Okay, almost a no-brainer there. The integral of a sum is the sum of the integrals. Okay. Okay, for positive functions. Do they draw a picture? Probably. F and G, right? Okay. Yeah, so the area under G and the area under F, okay, is shown in the gold. And then the blue would be the sum of the areas, right? Basically take the area under F and just tack it on top of the figure formed by the area under G. So this is just graphical addition. Graphical addition. Okay, and so here's kind of the proof. The way you would prove that the definite integral of the sum of functions, you just use the definition. Okay, so it's the infinite limit of the sums of the rectangles. Then you take the delta x and you distribute it to each of the terms, okay, in brackets. And then you take the the limit sum operator. I guess we could call this the limit sum operator. And you distribute it term by term, and then by definition, you take the limit sum operator and convert it to a integral operator. Okay, so there's the proof of property 2. And the same holds for subtraction as well. Okay. Okay, proved in a similar manner, yeah. Same. Okay, so use the properties of integrals to evaluate this, okay? All right, so the definite integral from 1 to 0 of 4 plus 3x squared. Okay, so we can distribute the integral operator term by term in the sum, like so. And then we can take the constant 3 out, okay, of the second term in the sum. Now, we know that this is 4 is a constant, so this integral will be 4 times 1 minus 0, okay? So that's just 4. And then this would be 3 times the definite integral from 0 to 1 of x squared. And in the lecture 5.1, we showed that that was a third. Okay, so the answer would be 4 plus 1. So this is 5. Okay, so now we can do more complex type definite integral problems. Okay, so that's 5. Okay, so for sure you'll have web assigned questions like that. Oh, okay. This property tells us how we can split an integral. Now, knowing that definite integrals are simply sums, we can find a point C between A and B on the interval of integration, and we can split the integral at some value between A and B. Okay, so for instance, as long as you have this kind of arrangement, okay, C is greater than A and C is less than B, so this is called splitting the integral. Okay, and this might be particularly useful if C is a vertical asymptote, or not a vertical asymptote, but a jump discontinuity exists at C. You basically can integrate around a jump discontinuity. Yeah, not easy to prove. So we won't. Yeah, so here they say, okay, the cumulative area, purple plus gold, is equal to the cumulative area. Provided that f of x is continuous and above the x-axis, it's easy to prove that case. Actually, you'll need something like Rawls' theorem to prove it, but we won't do that. Okay. Properties of integrals. Okay, so if we have the definite integral from 0 to 10 of a function is 17, and the definite integral from 0 to 8 of a function is 12, what is the from 8 to 10? All right, so so what we can do to solve this is we can use that property we just talked about. We can write this, so we have the definite integral from 0 to 8 of f of x dx plus the definite integral from 8 to 10. You see how the 8's are lined diagonally? From 8 to 10 of f of x dx is equal to the definite integral from 0 to 10 of f of x dx. Okay, and we know that this is 17, and we know that this is 12. So this would have to be 5. So that equals to 5, like so. Okay, so anticipate web-assigned questions like this, and perhaps, and most likely, a final exam question like this as well. All right. So 5, right? Okay, just like lining it up with the property. So slide 96. Okay, comparison properties. Okay, comparison properties, that means we have inequalities with integrals. So if f of x is greater than 0 on the closed interval, then the definite integral, of course, will be greater than 0, the area under the curve. If f of x is greater than g of x on this interval, then the area under the curve for f of x will be greater than the area under the curve for g of x. Stands to reason. Okay, and this doesn't matter if f of x is below or above the x-axis or a combination of both, just as long as f of x is greater than g of x. If f of x is wedged between a lower bound and an upper bound on a closed interval, then the area is bounded below by the area of this rectangle and above by the area of this rectangle. Okay, so those are very useful properties. We'll have some web-assigned questions leveraging those. So let's talk about property 6. Maybe there's a graphical rendition of it. So if f of x is greater than 0 on a closed interval, then it's definite integral. Okay. So we need a picture, guys. Yeah, no picture. Property 7, f of x greater than g of x. Okay. The bigger function has a bigger integral because f minus g is greater than 0. Yeah. All right, so that's how you can demonstrate that. F minus g will be greater than 0, and so the area under the curve of f minus g will be positive. 8. Okay, so in this case, this is interesting. Here we have f of x being bounded below by y equals m and above by y equals big M on the interval a to b. So that means that the area under the purple curve, under this lavender color, okay, the lavender color plus the purple color would be the area under y equals f of x. Okay, so that area, of course, is greater than the area under the purple curve. And then, of course, the area under M would include this white space plus this pink space plus this, or lavender space plus this purple space. And so that's an upper bound for the area under the curve. So we actually can establish lower and upper bounds for definite integrals. So this is a very useful picture to show. And that of course, assumes that f of x is greater than 0 on the interval. If it's not, then we'll have to do other things. Yeah, so we could take m and m to be the absolute min and absolute maximum value. So we can use the extreme value theorem to calculate lowercase m and uppercase m. See, in this case, uppercase m is the absolute max on the interval, lowercase m is the absolute min on the interval, and then we can use those as estimates for the boundaries of the integrals. Okay. The area under the graph of f is greater than the area under the rectangle with height m, and less than the area. Okay, yeah, so they keep repeating themselves in these slides. Okay, so we have this. So using property 1, okay, yeah, and so forth. All right, so there's kind of a proof using the properties. I guess I give an example, right? Estimating the area under curve using the extreme value properties using the rough estimate of the size of the interval without using the midpoint rule. So come on, give us an example. 106, please give us. Okay, yeah. So we're going to use that property to estimate the area under the curve from 0 to 1 of e to the x squared. So e to the minus x squared is a decreasing function on 0 to 1. Okay. So e to the minus x squared is going to look something like this. Okay, decreasing function. Here's 1. So its absolute max occurs at 1, and its absolute min occurs at e to the minus 1. Okay, so these would establish your big M and little m. So so we have then that using the theorem, we would have this result. By the property. Okay, and since it's a decreasing function, the maximal value occurs at the left endpoint, so that would be at x equals 0. At x equals 0, we would have 1 over e to the 0, which is 1, and the length of the interval is 1. Okay, so that's 1. So we know that this integral is less than 1. This definite integral will be less than 1. And then the lower bound occurs at x equals 1. And so that's 1 over e. So somewhere between 1 over e, which is a third, and 1 would be the evaluation of this integral. So it lies between a third and 1. So we would have to use further refinements in the midpoint rule to calculate a more concise value and probably take limits and so forth. So between the third and the 1 would be a good estimate. It's probably shown on the next slide. Yeah, 1 over e to 1. 1 over e is 0.3679. So between 0.367, 368, and 1. And this will be there will be a question like this on the final exam. And so here's the example. Yeah, here's the graph. Y equals e to the negative x squared. Okay, and you can see there's the graphical illustration. Okay, so this concludes section 5.2 of the lecture. So you'll midpoint rules, evaluation of definite integrals using infinite limits of sums. So you'll have quite a few web assigned questions on this topic. So I would suggest getting started as soon as possible for this content, this subject matter. Right. So end of lecture.